Graph theory turns networks, roads, friendships, circuits into precise mathematical objects you can prove things about. A graph written G equals open bracket V comma E close bracket is just a set of vertices V, the dots, and a set of edges E, the lines connecting pairs of those dots. The degree of a vertex V written deg of V counts how many edges touch that vertex. A tree is a special kind of graph, one that's connected, meaning you can get from any vertex to any other, and has no cycles, no way to walk in a loop back to where you started. The single most important theorem in this whole section is the Handshake Theorem. The sum of the degrees of every vertex, added up over the entire graph, equals exactly 2 times the number of edges. A direct corollary falls straight out of this. The number of odd degree vertices in any graph is always even, never odd. Tree edge count is beautifully simple. A tree with n vertices always has exactly n minus 1 edges, no more, no less. Then there are the 2 Euler theorems. An Euler path exists if and only if the graph is connected and has exactly 0 or 2 vertices of odd degree. An Euler circuit, a path that returns to where it started, exists if and only if the graph is connected, and every single vertex has even degree with 0 exceptions. Let's prove the Handshake Theorem. Every single edge in the graph has exactly 2 endpoints, so each edge contributes exactly 2 to the running total of the degree sum, 1 contribution to each of its 2 endpoints. Now sum this contribution over every edge in the entire graph. Since each of the edges contributes exactly 2, the total degree sum across all vertices equals 2 times the number of edges. Proof complete. The corollary follows almost immediately. 2 times the number of edges is always an even number, and a sum of integers can only be even if the count of odd numbers within that sum is itself even, so the number of odd degree vertices must be even. Here is the intuition behind why the Euler conditions work. Imagine walking through the graph, tracing every edge exactly once. Every time you arrive at a vertex partway through your walk, other than your very first starting vertex or your very last ending vertex, you have to both enter along one edge and leave along a different edge, and those 2 edges get used up in a matched pair. That requirement, entering and leaving in pairs, forces every pass-through vertex to have an even degree. The only vertices allowed to have an odd degree are the start and the end of your walk, each of which gets 1 single unmatched edge. Here's the trick, and it resolves almost every problem in this section instantly. Before attempting anything else, write the degree of every single vertex directly onto the diagram. Nearly every graph theorem you'll meet at this level comes down entirely to the pattern of which degrees are odd and which are even. Worked example A. A graph has vertices with degrees 4, 4, 3, 3, and 2. Does an Euler path exist? Step 1. Identify the odd degree vertices. The 2 vertices with degree 3 are odd, everything else is even, so exactly 2 vertices have odd degree. Step 2. The rule for an Euler path requires exactly 0 or 2 odd degree vertices, and we have exactly 2, so yes, an Euler path exists, and it must start at one of those 2 odd degree vertices and end at the other. As a sanity check, the degree sum here is 4 plus 4 plus 3 plus 3 plus 2 equals 16, an even number, exactly as the Handshake Theorem requires. Worked example B. A graph has 4 vertices, all with degree 4. Does an Euler circuit exist? Every single vertex has even degree, 0 exceptions. So yes, an Euler circuit exists. A closed walk using every edge exactly once and returning to the start. Worked example C, a direct Handshake Theorem check. A graph has 5 edges. What must the sum of all vertex degrees equal? Apply the Handshake Theorem directly. The degree sum equals 2 times the number of edges, that is 2 times 5 equals 10. Worked example D, tree edge counting. A tree has 12 vertices. How many edges does it have? Apply the tree edge count theorem directly. Edges equals n minus 1 equals 12 minus 1 equals 11. Common mistakes to watch for. First, and this is the single most frequent mix-up in this entire topic, confusing the Euler path condition, 0 or 2 odd vertices, with the Euler circuit condition, which is stricter, requiring 0 odd vertices, meaning all vertices even. Second, forgetting that the graph must be connected for either theorem to apply at all. A disconnected graph can satisfy the degree conditions perfectly and still have no Euler path or circuit, because you simply can't walk between the separate pieces. And third, miscounting the degree of a vertex when an edge loops back to the same vertex it started from. A loop usually counts as contributing 2 to that vertex's degree, not 1, since both of its endpoints sit at the same place.